So in this video, I'm going to go over a simple induction problem to help you understand the concept of induction. So to start, we have a theorem. This is our theorem. This is what we're trying to prove using induction. Induction is a proof method that has two concepts. It has a base case, and it has the inductive step. So let's do the base case first. So you might have seen this theorem. It states that 1 plus 2 plus all the way to n is equal to n times n plus 1 over 2. It's a simple way to calculate the sum of any n number of integers from 1 to n. So our base case, in this case, would be n is equal to 1. So we make sure that this theorem is valid for n is equal to 1. So on the left side, we have 1 is equal to 1 times 1 plus 1 over 2 on the right side. On the left side, we have 1 because it says 1 plus 2 plus all the way to n. But if n is only equal to 1, that means this 2 is not there, and the whole left side just becomes 1. So 1 is equal to, and then we substitute 1 for n on the right side here. So we get 1 times 1 plus 1 over 2. Now to simplify the right side, this becomes 1 times 2 over 2. And the 2's cancel out, and we're left with 1. So 1 is equal to 1. So now we've satisfied the base case. We've proven this theorem for n is equal to 1. But we want to prove the theorem for n is equal to 1, 2, and all other increasing n's. So how do we do that? Here comes the inductive step. So this step basically assumes that our theorem holds true for n is equal to k. And using that information, we now have to prove that the theorem is true for n is equal to k plus 1. So therefore, if we assume that the theorem is true for n is equal to 1, which we know because we just proved the base case, then we know that the theorem will be true for n is equal to 1 plus 1, which is n is equal to 2. And because we know that the theorem is true for n is equal to 2, we now know that the theorem will be true for n is equal to 3 as well. So therefore, we can prove it for all n integers greater than 1. So now we just have to complete the inductive step. The way we do this is we first substitute k for our theorem. So we have 1 plus 2 plus all the way to k is equal to k times k plus 1 over 2. We just substituted k for n in our theorem. This is our assumption. Now we need to prove this. We need to prove that 1 plus 2 plus all the way to k plus 1, this is our proof right here, when n is equal to k plus 1, is equal to, and here's our formula, so we use this formula right here. Is equal to k plus 1. We substitute k plus 1 for n, and k plus 1 over 2. So I just substituted k plus 1 for our n here. So this is our assumption, and this we have to prove. So how we solve these problems is we use our assumption to prove our theorem for k plus 1. So we recognize that on the left side of our proof, 1 plus 2 plus, we know that this left side of this is actually included in this, because 1 plus 2 plus k plus k plus 1 is another way to rewrite this. And this is the same thing as this. So we can substitute k times k plus 1 over 2 for this quantity right here. So let's do that. K times k plus 1 over 2 plus k plus 1. And that's equal to k plus 1. And this right over here can be simplified to k plus 2 over 2. Now what we can do is we can multiply this k plus 1 right here, top and bottom, by 2. So we can do this, 2 times k plus 1 over 2. And we do this because we want all the denominators to have a 2. That just makes the algebra easier. Now we do this, k times k plus 1 over 2 plus 2 times k plus 1 over 2. Now we have a common factor here, a k plus 1 factor. We have k times k plus 1 and 2 times k plus 1. So now we can factor this into k plus 2 times k plus 1. Basically just factoring the k plus 2 into one expression. And that is divided by 2. And that equals, on the right side, k plus 1 times k plus 2 over 2. And these two quantities are equal. So now we have completed our proof by induction. We have proven that the left side is equal to the right side, and thus the theorem, if we assume n is equal to k, holds for n is equal to k plus 1 as well.